operation, and I've tried to use that experience to build a PhD project at Colorado School of Mines. So why don't I go ahead and get sharing here. Okay, can everyone see my screen and hear me? Oh, cool.
Screen just went away.
Are we all good there?
We're still not seeing your screen.
Still not seeing the screen. Let me try to start the slideshow first. Is that working?
Yeah, here it comes. We've got it.
You got it?
Yes, looks good.
Perfect. Awesome. Great. Yeah, so today we'll be talking about kind of an introduction to geothermal energy, since it's kind of a catch-all term for a lot of different technologies. And then we'll dive into my PhD project, which is a case study on the Texas Gulf Coast. So to get started, I like to start by discussing, an overview of geothermal and the geothermal resources here in the U.S. The map on the left is from NREL, the National Renewable Energy Lab here in Golden, Colorado. It's a little outdated. It's from 2016, but it still gets the same point across, showing which states produce geothermal energy and how much they currently have installed. Again, this is a little outdated. These numbers have probably gone up a little bit since 2016. But roughly, we're at about 3.5 gigawatts of installed geothermal capacity to generate electricity here in the U.S. And of course, mainly from the western U.S. states. Over here, this is from the EIA. It is showing the breakdown of what fuels we use to generate electricity. Of course, natural gas, coal, and nuclear really dominate, how we make our electricity here in the U.S. And this renewables number has probably gone up since this was published in 2021 with the amount of investment in wind and solar over the past couple of years. And I like to point out geothermal as of 2021, despite having 3.5 gigawatts of installed capacity, is still less than 0.5% of our overall energy portfolio. This is another graph from EIA that just shows that breakdown in a different way. We use about just over 4 terawatts of electricity here in the US, which is a lot of energy. And you can see that breakdown, how it's changed through time up to 2020. And then up here is another graph from, I think, Augustine 2017 that shows the distribution of the average installation costs in dollar per kilowatt of these different energy sources. Of course, our combustion turbines for natural gas are the cheapest right now. Solar and wind kind of fall in the middle. And then, of course, what we're going to be talking about today are sedimentary geothermal. And as of now, those are pretty expensive to develop. And consequently, we haven't really developed any of these in the US, but it's still a potential energy source we need to be discussing. And again, as of 2020, the US is actually the largest producer of geothermal energy in the world. You think about countries like Indonesia, the Philippines, Iceland on here, who produce a lot of their power from geothermal energy, but we still produce more here in the US. Okay, so what is geothermal? And I'm going to go through a short introduction on geothermal, just because it is a catch-all term for a lot of different things. And so, of course, geothermal is earth heat, or heat from the earth. And this figure over here on the left, it's a really great figure. I always include it on my introductory geothermal presentations. It's from this GeoVision report. And if you're interested in geothermal, I encourage you to reach out or to just go Google this GeoVision 2017 report. It's published by the Department of Energy, and it does a great job of summarizing everything geothermal. So it's a great place to start. And a lot of the figures I'm going to show in the next couple slides are from this report. And so geothermal encompasses a lot of different things. It can talk about geothermal heat pumps, which you might be familiar with, which are just a series of tubes or wells you can install under your house or your business or campuses to basically take waste heat and store it in the soil and extract it when needed. That's considered geothermal. And then, of course, on the opposite end of the spectrum, you have your hydrothermal or your conventional hydrothermal systems. And these are what you probably think of when you think of generating electricity from geothermal. Places like Iceland or Hawaii or Indonesia, where you have these large volcanic provinces, we can drill wells, adjacent to volcanic activity, produce steam directly out of the ground, and use that to spin turbines and make electricity. And that's considered conventional hydrothermal. So these are very hot, permeable resources that we can develop using existing technologies. And from the oil and gas side of things, we can start to think about these different resources as, conventional and unconventional, just like we would think about different oil and gas resources. So on the unconventional side of things, we have what are called enhanced geothermal systems. And these are geothermal reservoirs where maybe they're not quite as hot as these conventional hydrothermal systems, or they're hot, but they're low permeability and have a low fluid saturation. So either have to stimulate the wells with hydraulic fracturing, or we'll have to pump water down to heat up and to be extracted. And so that's considered more of an unconventional style of geothermal. And then we have what's called direct use applications. And that's simply just using these hot fluids that are coming out of the ground for heating and cooling in residential, commercial, and industrial applications. What this diagram doesn't really have is anything about sedimentary geothermal, and that's particularly what I'm interested in, as having a background in sedimentology and stratigraphy, and coming from the oil and gas side of things, I got interested in geothermal and sedimentary basins. And it's the same principle that we talked about with these hydrothermal and enhanced geothermal systems. It's using these hot, deep brines in these basins for either electrical power generation or a direct use application. There's also a term called blind geothermal systems, and these are subsurface geothermal systems with no surface expression. So typically with these hydrothermal systems in these volcanic provinces, you'll see hot springs or fumaroles, geysers, mineralization along faults, things like that. And when you see that, you can think, well, we probably have a hydrothermal resource below. But in these sedimentary basins and with these enhanced geothermal systems, we don't have those surface expressions. So they're a little bit harder to find and locate. So in terms of types of geothermal reservoirs, all types of reservoirs can be used for geothermal. In our conventional hydrothermal systems, they can be igneous, metamorphic, or sedimentary. When I was working oil and gas and coming into geothermal, I didn't think that the sedimentary rocks really fell into this conventional hydrothermal category, but some of the power plants in California that are these conventional hydrothermal systems actually produce steam from hot sandstones, which is interesting. As far as enhanced geothermal systems go, these are typically igneous or metamorphic rocks, hot, dry rocks that we can drill into, hydraulically fracture, and build this fracture network reservoir that we can use. I was talking to a company yesterday about potentially doing this in some sedimentary rocks that are tight, so maybe that'll be added here in the EGS category. In terms of sedimentary basin geothermal, carbonates, siliciclastics, and potentially evaporites can be used for geothermal energy. And in all of these reservoirs, fractures are very important because we do need a lot of fluid to the surface to be able to make electricity. On the right here, we have another diagram from GeoVision that shows some of these different uses based off temperature. Our conventional hydrothermal resources fall into this very hot category. Typically, that's just used for power generation or hydrogen production. And then our unconventional EGS and sedimentary basin geothermal more falls into this kind of a mid-range temperature category. We're really looking around 250 to 300 degrees Fahrenheit in these sedimentary basins. And then below those temperatures, we have all these different direct use applications that we can use that thermal energy for besides making electricity. The last thing I want to talk about with direct use before we dive into electrical power generation are some of the different direct use applications here in the US. And this is from 2017. But these are some of the different uses as of then. Of course, we've probably all been to hot springs, pools that are heated with geothermal energy. There's district heating, so tying in towns and campuses to geothermal sources. There's space heating, greenhouses, and of course, aquaculture. So there's a lot of different uses for thermal energy here in the US. Moving into the conventional hydrothermal systems, this is another figure from the GeoVision report. And the conventional systems are a little bit easier to wrap your head around. Of course, we have some sort of heat source related to volcanism or magmatism down in the subsurface that's providing heat into some sort of fracture system that's filled with water. And we can drill production wells into this fracture network or these somewhat porous reservoirs, produce steam directly out of the ground, run that through a power plant to make electricity, and then we can re-inject either the steam again or condensed water back underground. And typically with these power plants, they like to produce from the hot side of the system and re-inject into the cool side, kind of creating this convective loop. And that's your conventional hydrothermal systems. This is a picture I took of the Krafla geothermal power plant in Iceland when I was there last year. And coming from the oil and gas side of things, these geothermal fields, often resemble our conventional oil and gas fields. We have a series of production wells feeding into pipelines that go to a central processing facility, and then that goes into a power plant to make electricity. I was actually there on my birthday because I'm a big geology nerd, exploring geothermal power plants and resources in Iceland. But yeah, this power plant produces 60 megawatts of electricity, and it's been producing since about 1997. And with these conventional systems, there's really two types of power plants. You use your dry steam power plant, where you're producing that steam directly out of the ground, running it through a turbine, using that turbine, or spinning a generator with that turbine to produce electricity, and then you can re-inject that steam or cooled water. Or you have to use what's called a flash steam power plant. If you have a multi-phase system where you're producing water and steam out of the ground, you have to separate the steam from the water, because you don't want water going through your turbine. So you separate the water out, and you can actually, I was at a power plant in Reno this summer, and they actually installed additional low temperature power plant on this side of the flash tank to further increase the efficiency of these power plants. And so that's what's typically used for conventional systems. I do want to talk about the Geysers hydrothermal power plant in California. It's actually kind of the largest geothermal power plant, I think, in the world, if not just in the US, but it's 13 geothermal power plants that are kind of interconnected. They have 319 steam wells, 73 injection wells. They drilled their first well in 1920. The average reservoir depth is about 8,500 feet. And they produce 630 net megawatts of power from these power plants. And, it's kind of interesting. A lot of these geothermal systems share kind of the broad elements to our classic petroleum systems elements. In this particular situation, they do have a reservoir caprock here, our top seal, and they produce steam from this permeable reservoir and use that to make electricity. So there really is a lot of overlap between these geothermal systems and what we've been doing in oil and gas for a long time. As far as enhanced geothermal systems go, this is another GeoVision diagram. And with these enhanced geothermal systems, typically you drill a well couplet. So you have a production and an injection well. And you drill your production well and you fracture stimulate the hot, dry rock down here. And then you can pump down water that'll heat up in this fracture network. And then you can pump it out through your production well and use that in a specialized power plant to make electricity. There's a couple ongoing projects here in the US. Kind of the more famous one is this Utah Forge project, which some of you may have heard of. It's a cross collaboration between the Department of Energy and just a ton of universities, national labs, and industries. But basically, they drilled 2 wells down into this granitic basement, and they're trying to circulate water between the wells and bring it back to the surface to make electricity. It's very interesting. And in these sort of situations and in sedimentary geothermal, we can't use those conventional power plants because the water's not hot enough. It's not coming out as pressurized steam. So we have to use what's called a binary cycle power plant, or you might have seen what's called an organic Rankine style power plant. And with these, we produce the hot brine out of the ground, and we run it through a specialized heat exchanger that transfers the thermal energy from the brine to a working fluid. And a working fluid is just a fluid that has a low vapor pressure that turns to gas or steam and creates pressure, and we use that pressure to spin a turbine and a generator and generate electricity. And so the working fluid just stays within the power plant, and the brine is pumped through the heat exchanger and then re-injected back into the ground to heat up. An example of sedimentary basin geothermal is from this Deep Corporation up in Canada, and they've drilled a series of these horizontal well couplets into what's the name of the formation? The basal sandstone in the Williston Basin. So they're operating in southern Saskatchewan, and they're actually producing hot water from this formation, bringing it up to their power plant to generate electricity, and they're re-injecting it back into that same formation via horizontal wells. So it's a very interesting ongoing project. As far as well designs and fluid types go, I briefly touched about this on the last couple of slides. You know, we're all familiar with brines. These are just hot saline formation waters that are stored in these underground reservoirs and sedimentary basins. But working fluids are either a gas or a liquid that we can transfer thermal energy to or transfer from one source to another. People have talked about using supercritical CO2, but more commonly we use butane or ammonia or other type of hydrocarbon-based fluids there. As far as well designs go, open loop wells, these are what we're all familiar with in oil and gas. These are perforated wells where we can either extract fluids from a reservoir or re-inject back into them. The geothermal industry calls these open loop. But then we have closed loop wells, which these are fully cased wells where we can circulate a working fluid through to extract thermal energy. And the fluid never interacts with the formation, and the formation fluids never interact with the anything inside the wellbore. And this is an example from a company called Greenfire Energy. They have this sort of hybrid system where they would drill a perforated well, allow hot brine to come into the bottom, and they could put this downhole heat exchanger in there to extract thermal energy from this wellbore. Another design comes from another company called Ever, where they drilled a horizontal well, intersected a vertical well to create this loop system, and they can circulate a working fluid through this well to extract thermal energy from the subsurface. So both very interesting projects, but these are examples of what are called closed loop systems. Okay, so let's move on to sedimentary basins and why I'm interested particularly in the Gulf Coast. And so this is a map from the SMU Geothermal Laboratory. It's temperature at 6.5 kilometers, or about 21,000 feet. And if you're not familiar with the work done by SMU over the past 15 or 20 years, and you're interested in geothermal, go look at the work they've done. It's a really great place to learn from. But I like this map because it really highlights the hot areas of the U.S. Of course, the western U.S. is very hot. There's active volcanism, ongoing extinction, things like that provide a lot of heat flow and thermal energy into these areas. Of course, we have the volcanism in the Cascades, the Yellowstone hotspot, Basin and Range extension, the Salton Sea area, and of course the Rio Grande Rift, all products of thermal energy and active tectonism. But when I looked at this map, the Williston Basin, the Denver Basin, and the Gulf Coast really popped out to me because these are places where we don't have active volcanism or ongoing tectonics, but they're kind of abnormally warm sedimentary basins compared to others, like the Anadarko Basin, which really isn't showing up here, things like that. So we're going to focus in on the Gulf Coast for the remainder of this presentation. And to finish up, once we're in these sedimentary basins, there's a couple different ways we can try to go after geothermal. Some of the low-hanging fruit that's been discussed as well is there just co-production with oil and gas operations. We're already producing hot water out of some of these oil and gas fields that's just being pulled off at the separator and probably re-injected. Can we do something with that hot water? Can we use it for heating and cooling, or can we use it to generate electricity? And so some of the advantages here, it's of course lower cost because we already have the wells and the infrastructure in place, and we know the temperatures because we've drilled a lot of wells into these fields. But the key disadvantages are the well locations. You know, these were drilled for oil and gas, so if we get lucky and the reservoirs are hot enough where we can use it for geothermal, that's great, but that's not going to happen all the time. Second, we can repurpose some of these existing oil and gas wells that meet these criteria. If these reservoirs or formations are hot enough, we can convert those well bores to be geothermal wells when these wells reach the end of their production life. Or we could maybe go back and recomplete or extend some of these wells into some deeper formations to produce geothermal energy. Again, it's somewhat lower cost because, like with the previous example, we already have the wells and infrastructure in place, and the same disadvantages, though they were drilled for oil and gas, not necessarily for geothermal. So the next option, of course, is exploration for new geothermal fields. And of course, with this, we can pinpoint exactly where we want to drill. We can target the exact formations we want. We can drill specific types of wells, horizontal, vertical, combination, wide diameter wells, etc. But of course, the key disadvantage is here. This is the most expensive and risky option for geothermal in these sedimentary basins. And so what are we exploring for? This is a graph from Augustine 2017, which I think does a good job of kind of providing a high-level overview of what we actually need to make electricity from hot brine in sedimentary basins. So I have temperature here in Fahrenheit on the x-axis and flow rate in barrels per day on the y-axis. And each one of these colored curves represents different amounts of electricity. So this green curve represents 4 megawatts of electricity. And so what this publication is suggesting that at about 300 degrees Fahrenheit, we need about 65,000 barrels per day of total fluid to make 4 megawatts of electricity, which is a lot of water, obviously. And as you decrease the temperature, let's say to 250 degrees Fahrenheit, you need over twice as much to produce the same amount of electricity. So temperature really drives efficiency here. But regardless, you still need a lot of hot water, hot brine to make electricity. So in order to do that, of course, we need high temperatures. 250 degrees is about the minimum cutoff, depending on different variables and input parameters with these power plants and reservoirs. Of course, we need reservoir deliverability and storage capacity. So, high porosity reservoirs that are thick with hundreds of millidarcies of permeability to get these flow rates, and of course, fracture permeability, whether that's natural or engineered. Pressure is kind of a double-edged sword. Pressure is good for lifting brine from the deep reservoirs because oftentimes to find these high temperatures, they're in the bottom parts of these basins, the deepest parts of these basins. But then if you're going to have a high pressure reservoir, it's going to be hard to re-inject back into that reservoir. You're going to end up having a lot of parasitic loss using electricity to re-inject into these high pressure reservoirs. Alternatively, low pressure is good for re-injection capabilities, but you're going to have to, of course, burn some electricity pumping that water from these deep reservoirs. Looking at the Gulf Coast now, this is a great Gulf Coast diagram that just shows the complexity of the Gulf Coast basin, all the different sub-provinces, uplifts, and basins. And so for the remainder of the presentation, we're going to be focused down here in the Rio Grande embayment area of the Gulf Coast. But as you can imagine, exploring for geothermal resources down here in South Texas is probably going to be different based off the formations and the structures and the tectonic history as compared to like the East Texas basin or something over here in Mississippi. So it's a complicated basin to explore in. For those of you not too familiar with the Gulf Coast tectonic and depositional history, I'm going to go through the highest level overview I can, which is going to skip a lot of things. But basically, the Triassic through early Jurassic, that's where we see our extension and rifting, and the formations and rocks down there reflect that. And it's not really until we move into our upper Jurassic to lower Cretaceous is really when we start to develop the Gulf Coast into the passive margin that it is today. And so basically we have a deposition from the Triassic through the Quaternary across the entire Gulf Coast basin. And I like this strat column because it shows that pretty much everything on the Gulf Coast is a gas or oil producing formation. And we have just an enormous amount of source rocks out here too. And in my mind, one day we'll have another column here that shows which ones have geothermal energy potential. So now I want to talk about the Texas Gulf Coast and some of the key geothermal elements, or at least what I'm considering some of the key geothermal elements. And the first one is the depth to 250 degrees Fahrenheit. And these two maps are from another SMU publication, Blackwell et al. 2010, where they went and mapped some of these different isotherms across the Texas Gulf Coast. And so I extracted the depths to 250 degrees Fahrenheit and put them on this map over here. And that shows that roughly 250 degrees occurs around 9,000 feet in South Texas and East Texas with this kind of peach color, and then around 10,000 feet across the rest of the Gulf Coast trend. And that's that important number because that is the considered an approximate minimum temperature for electrical power generation. So that's an important geothermal element of the Gulf Coast. Secondly, talking about geopressure geothermal systems. And these are pretty interesting. These were originally defined as potential geothermal resources in the 1970s and 80s by the Bureau of Economic Geology of Texas and Department of Energy, where we have these highly overpressured zones in these Paleogene formations, and they're very hot, and we can use those for geothermal energy. And the location of these in the Wilcox, Blue, and Frio formations are shown in these striped polygons across the Texas Gulf Coast. Basically what these are, we have these enormous growth faults that occur during deposition of these different formations that lead these sandstones to be just extremely overpressured. They're basically at geopressure levels. And in the late 1970s, the Department of Energy and Bureau of Economic Geology actually drilled into one of these for geothermal energy, this Pleasant Bayou well, just south of Houston. And between the hot water they produced and the methane that they produced, they were able to produce about 1 megawatt of electricity from this vertical well that only perfed like a 60-foot zone in this sandstone. So it was a great proof of concept for geothermal energy on the Gulf Coast and in these hot sedimentary aquifers. Another key geothermal element is these lower Cretaceous shelf margins. And those are shown as these blue and green lines across the Gulf Coast. And these are important because our porous, impermeable lower Cretaceous reservoirs often are all north of these shelf margins, as shown as from this diagram from Ewing and Galloway. Another key geothermal element are the location of salt diapirs. And salt diapirs are very interesting. There's over 80 of them on the Texas Gulf Coast alone. They were first kind of discussed as a source of geothermal energy in the 1970s. And what's interesting about them is they are dominantly composed of halite, and halite has a much higher thermal conductivity as compared to the surrounding siliciclastic and carbonate rocks. So the question is, well, can we actually target these diapirs for their thermal energy? Can we, drill into them and extract thermal energy? Or can we look for heat anomalies in the reservoirs above and adjacent to them? Because these diapirs often kind of wick heat from the rocks below them and cause thermal anomalies in reservoirs just above and adjacent to the top of them. So can we look for geothermal resources above or within these diapirs? And the fifth element that I think is very important out here are the type of crustal types along the Gulf Coast. This is another figure from Ewing and Galloway 2019, where they're showing the different crustal types beneath all of the Gulf Basin. And so most of Texas is underlain by the Proterozoic craton. But as we move onto the Gulf Coast, we see this zone that's underlain by this thick transitional crust, and in the southern part of the coast and the shelf is underlain by this thin transitional crust. And so how does that affect where we're going to explore for geothermal resources? The heat in this basin is coming from radiogenic decay in these different crustal types that's feeding heat up into the basin, since the Triassic. So how does that these different crustal types affect the distribution of heat and thermal energy in this basin? So combining all of these together, you get a map that looks like this, where we have all of these different geothermal elements overlapping. And then based off that, to start my PhD project, I identified these 4 areas of interest. This Sabine uplift AOI, where we have this large uplifted crustal block that brings higher temperatures closer to the surface. We have the East Texas AOI, which is this East Texas salt basin, which is just a region that contains an abundant amount of salt diapirs. We have this North Houston AOI, which is one of these large overpressured zones in the Wilcox Formation beneath Houston, which is kind of interesting for its kind of economic perspective. And then we have the South Texas AOI, which ultimately I chose to do my PhD project down here. And we're going to be talking about that area for the remainder of this presentation because it has all of these elements overlapping. It has the shallowest depth of 250 degrees Fahrenheit, as previously mapped from SMU. These geopressured zones, Cretaceous and Jurassic formations that are well above 250 degrees Fahrenheit, and they're porous and permeable in some places. Multiple salt diapirs, and these kind of transition between these different crustal types. So zooming into South Texas, this is all the same map elements on here, except for the crustal type. I don't have that on here. But that shows that, this area is cross-cut by that shallower depth to 250 degrees Fahrenheit here, and it's a little deeper to the north and the south. These two blue zones are those overpressured zones in the Paleocene to Eocene Wilcox Formation. These yellow polygons are those different salt diapirs across the area, and these blue and green lines are the Aptian and Albian shelf margins. And so this is a well log based project that I'm working. I work in an oil and gas research group doing geothermal. And so we have a lot of companies that sponsor our research. So we have access to a lot of well data. So this is a well log based project. I put together a data set of just over 3,400 vertical wells with digital logs deeper than 7,000 feet to use for this project. Where 250 degrees occurs about 9,000 feet, we have just over 3,000 wells to use. And you can see how the amount of wells drops off with depth. But we do have a couple wells that were drilled deeper than 20,000 feet out here, which is very interesting for the onshore world. For temperature data, I put together a data set of almost 1,600 vertical wells with one or multiple bottom hole temperature measurements, and that's shown here on this temperature and depth plot, and these are uncorrected temperatures. So diving into the Gulf Coast strata and type log and regional structure, this is the same strat column we have here that I showed earlier here on the left, and this is what I'm calling my Mesozoic type log. On the left here, I have gamma ray from 0 to 150. Where the blues and greens are lower gamma ray, and the grays and yellows are higher gamma ray. The blues and the greens in this Cretaceous and Jurassic section typically represent carbonates. This whole Mesozoic section is over 10,000 feet thick out here, so we have a lot of Cretaceous and Jurassic to look at. This is my deep resistivity from 2 to 200, scaled greater than, I think, 20 ohms. That's just for correlation purposes. And then here I have my bulk density log, where the blues and purples are higher bulk density, and the greens and yellows are lower bulk density. And these are the different formations we're going to be kind of looking at today. I put together a structure map on top of the Austin Chalk from 267 wells that penetrate the Austin Chalk here. Austin Chalk is a good marker horizon across the area. And what it's showing is we basically have homoclinal dip from northwest to southeast across the area, where it's more shallow to the north and deeper to the south. And all of these Cretaceous and Jurassic maps end at the shelf margin, because once we get south of there, the Cretaceous and Jurassic systems are below those thick expanded sections in the Paleogene, and they're just too deep and not penetrated. So let's take a look at this cross-section 8A prime, where I projected in my key petrophysical wells to show these structural and stratigraphic relationships. So I put together a stratigraphic framework basically from the surface down to those deep Jurassic formations, so I could really understand every formation that has geothermal potential out here. And so this is that northwest to southeast cross-section. It's about 70 miles long, and it's basically showing that all of these formations are roughly dipping off to the southeast. We have our lower Cretaceous Austin down here. We're not going to be talking about that today because we just lack a lot of well penetrations of it. We're going to be talking about the Sligo quite a bit. That's the kind of deepest Aptian carbonate formation that we penetrate out here. That's dipping off to the south. We have our Pearsall Shale thinning and dipping to the southeast here. Our Glenrose and Edwards carbonates here in different shades of green. Our upper Cretaceous formations I've just lumped into blue here. And then our Paleogene systems are out here in pink. And if we turn on our isotherms from the SMU maps, where it shows it's a little bit deeper to 250 degrees to the north and a little bit shallower to the south. That shows us that our aptian carbonates are getting into that 250 degree temperature window to the north. As we move south, we get into our Albian systems and our upper Cretaceous intervals as that isotherm kind of moves up. And you can kind of disregard this abrupt change in depth here. I'm using an equally spaced cross section to show these relationships, so kind of makes this look a little funky. And then as we get to the furthest southern part of the area, that's when our Paleogene systems first get into that 250 degree temperature window. And so based off that, you can say roughly that anything shallower than this, the formations that are up here, fall into that direct use zone where we could potentially use those brines just for their thermal energy. And it's not till you get below that where we might get into a low efficiency electrical power generation zone and then a higher efficiency electrical power generation zone. So what this looks like in map space, this is my 250 degree geothermal play fairway map, or you can kind of think of it like a subcrop map, where I'm mapping that intersection between these dipping formations and that isotherm, like this cartoon shows. And what's that showing is that the Sligo formation is the shallowest and youngest formation that we can target to the north, and all the formations get progressively younger as we move to the south, related to that dip and the way those isotherms are cross-cutting. So now moving into some of the play types to finish up here that I've identified. The first thing I'm interested in are these aptian and albian shelf margin reefs and shoals. These are two type logs from the Sligo system, that deeper albian carbonate system, one for my platform interior and one for my shelf margin. This is just your typical carbonate block diagram that shows what one of these Cretaceous carbonate systems might look like with your platform interior and your kind of platform shelf margin reefs and shoals here. Same type of log display here, gamma ray, resistivity, bulk density, but now I've done just kind of a back of the envelope density porosity on a limestone and dolomite matrix to try to highlight where some porosity might be in these formations. And this is where I see down here, you know, this might be some of our platform interior shoals that we might be able to target for geothermal energy. And then out at the shelf margin, we need to look for these shelf margin reefs and shoals out here for potential geothermal reservoirs. This is another cross section that runs basically northwest to southeast across the area. It follows roughly depositional and structural dip until it hits the shelf margin and then kind of goes along depositional strike here. The platform interior faces are shown in blue, and our shelf margin is shown here in gray, and our slope systems are here in green for the shelf margin complex. And this is what that cross section looks like. I've datum this, I flattened it on the top of the Sligo. So we can see our platform interior faces back here, our shelf margin reefs and shoals here, and then our slope system down here. It's important to note that the Sligo system out here ranges in depths from about 9,000 feet to the north to the top of the Sligo reef is about 16,000 feet at the shelf margin. So it is rather deep. But the bottom hole temperatures range from 250 degrees to the north to almost 375 degrees down here at the shelf margin. So this is a hot system down here. Moving up in section, looking at the Maastrichtian geothermal play types, I'm interested in the Olmos formation out here. The Olmos formation is about 100 to 150 feet thick across this part of South Texas. This is a large deltaic system that progrades across the area during the late Cretaceous. We see bottom hole temperatures above 250 degrees Fahrenheit in a lot of these wells along this trend. This particular well has an uncorrected bottom hole temperature of 257 degrees, and that's probably going to go up by a factor of about 20% after correction. And so there's two potential play types here. It's going off trend from some of these fields, looking for wet sands off structure and down dip, or repurposing some of these existing fields because there are quite a few oil and gas fields in this Olmos section. Of course, like I mentioned previously, the Paleogene geopressure geothermal systems are of interest out here. These hot, highly overpressured sandstones have been proven that you can make geothermal energy from them. So now we need to keep that exploration going and get out and start exploring in these. In some areas, the Wilcox, ranges in thickness from north of the main Wilcox fault zone, where we don't see any of the growth strata. It's just a couple 100 feet thick. And as we move into some of these down dip growth fault areas, the Wilcox can be 4,000 to 5,000 feet thick. So it's a lot of expansion across these growth faults. Bottom hole temperature for this particular well, which is in one of these geopressure zones, is 322, and that is, of course, uncorrected still. So that'll probably go up by another factor of 20%. There's 6 diapirs, salt diapirs within this area. They all range in depth, which is very interesting, from this Pangana diapir, which is basically at the surface, to this Pescadito diapir, which is buried down at 15,000 feet. Of course, they all have oil and gas production associated with the top of them. So can we actually go through and target some of these for geothermal energy, where maybe we can drill those closed loop wells into them, so we're not actually interacting with the salt, we're just extracting thermal energy, or we can look for those heat anomalies on top of them. And then to finish up, repurposing some of the existing oil and gas fields. And this is probably a PhD project, if not multiple ones in itself. Kind of north of the Albion Shelf margin, a lot of these Cretaceous fields are just too shallow. They're probably too cool to be repurposed. But when you get into this sort of Goldilocks zone between the Aptian and Albion Shelf margins, maybe we can start targeting some of these, or at least looking at some of these fields for repurposing. These are Edwards and Glen Rose carbonate shelf margin fields that are nearing their production life. And this is a very large oil and gas field in the Olmos Formation that has over 1,000 wells that are also nearing their production life. And all that infrastructure is already in place. We see bottom hole temperatures over 250 degrees Fahrenheit. How can we use these for geothermal energy? And in this area, I haven't had a chance to investigate. This is the main Wilcox trend. So these are mostly Wilcox gas wells in this area. And there's just a whole set of projects to be done looking at these fields for repurposing. And some of the repurposing methods, like I talked about before, we can just extend some of these wells or reuse the wells, or we can go down and put some of those downhole heat exchangers if the well bores are wide enough. So to finish up here, because I'm getting a little low on time, what we're seeing here, I put together this map to just show some of the kind of distribution of these different play types. In green here, we have those platform interior shelf margin reefs and shoals, or platform interior reefs and shoals. That's where I'm starting to see some of the porosity development in those Cretaceous carbonates. In gray here, these are these fields that I just talked about that we could potentially repurpose in different Cretaceous formations. This orange polygon is part of that almost delta system. So this would be kind of down dip and off structure from AWP field. Can we go after some porosity and potentially use that hot brine to make electricity down here? This blue here and along the Albion Shelf margin, these are those shelf margin reefs and shoals, areas where we have either ongoing gas production, or I see some of the porosity on those different logs that I've been working on. Of course, our geopressured zones in the Wilcox Formation here in blue, and then those yellow salt diapirs. So this is just a large area in South Texas that I'm working, but you can kind of imagine if we kept moving, out of this polygon that I've defined, you would start to see some more of these different polygons popping up in different formations based off reservoir characteristics, temperature and depth, things like that we could potentially target. So we really need to do a lot more work out here on the Gulf Coast to start exploring for these resources. And then to finish up here, I put together a block diagram to summary these the kind of geology of the Gulf Coast, these different play types and some of their potential uses. So these are the different play types that we just talked about, our shelf margin reefs and shoals, our Maastrichtian sandstones, salt diapirs, etc. But there's just a ton of uses for geothermal energy out here on the Gulf Coast. There's some publications from the 80s and 90s that talked about using hot water produced from some of these oil and gas fields for just heavy oil extraction. Of course, I mentioned repurposing these wells and fields too. There's power and thermal energy for direct air capture units. There's plenty of carbon sequestration companies that are looking at doing this on the Gulf Coast, and they're interested in geothermal to power and to provide thermal energy for those units. Of course, the big thing is utility scale electrical power generation, using these hot brines to make electricity and provide that to the grid. I think one of my favorites that I added on here recently is using the geothermal energy to produce green hydrogen that could be potentially used as rocket fuel. You know, the SpaceX Starbase is down here in South Texas, and I just think it's very interesting that we could potentially be using geothermal energy to, you know, explore space. Electrical power for data centers is a big thing that's popped up in the past year or two with AI, cloud data, everything like that. That requires a ton of energy. And then, of course, direct uses, just heating and cooling in residential, commercial, and industrial applications, or in especially here in Texas, in the refining or any other industrial applications. So that's all I have to talk about today. That's kind of a big summary of the Gulf Coast and the project I'm working on down in South Texas. And with that, I'll open it up to any questions. So thank you.
Thank you, Eric. That was excellent. And I think really exciting and fun, since we're familiar with a lot of those formations from oil and gas work. We've got a question in the chat from John McLeod. How are dissolved solids and brine that precipitate, including mineral scale and surface infrastructure, and economically addressed? He mentions in the 80s, the DOE defunded their failed Raft River geothermal project in southern Idaho for that reason. The surface infrastructure was moved to a hotter project in Nevada. Their TDS was considerably lower than typical geo and brine.
Yeah, I mean, that is, I think, across not just sedimentary geothermal, but across all geothermal for power generation. That's a big concern, scaling from these different brines and from the steam. How we tackle that, I mean, I think that's going to be formation by formation specific here in these hot sedimentary aquifers. But yeah, that's going to be one of the main challenges out here, I think. Having worked, I spent a lot of my career at Anadarko and Oxy working South Texas and East Texas, and we had some nasty brines that we would produce out of the Cotton Valley and other formations like that. So it's definitely one of the big risks with this sort of energy development, but it's also a risk in your conventional hydrothermal too, keeping the steam or brines kind of at their temperature and pressure that they would be in the subsurface to keep them from precipitating solids in your equipment.
And then we've also got another one from Juan Falquez. What methodology did you use to make BHD corrections for your data? What's the margin of error?
That is a great question. I actually have an entire another hour-long presentation we can go through on bottom hole temperature correction in South Texas from different methodologies and the error associated with that. So without getting into another hour-long discussion, I went with the kind of Waples bottom hole temperature correction methodology that uses times and circulation data, surface temperature, and depth to really try to, you know, correct for some of those parameters while we're logging. And with that data set, I saw about, like I mentioned a couple times in the presentation, about a 20% increase in uncorrected to corrected bottom hole temperatures, kind of across the board. There were some formations in the deeper Jurassic where it's a little bit different, and I think there's some different geothermal gradients going on down there that are affecting that. But that's the correction method I went with for this project. I also did, just for comparison purposes, I used 3 other correction methods, the Keel correction, the SMU Harrison, and another one, just to compare. And average statistically, bottom hole temperature correction for that same data set using those 4 different methods ranged from about 12% increase in temperature to about 20%, if that helps answer your question.
Okay, and I assume your primary source of the BHD data was log header data?
Yeah, it's all painfully came from, I would say days, but it was probably more like weeks of reading through and pulling off temperatures, dates, everything from well log headers.
Okay. Okay. We have any more questions from the audience? Feel free to raise your hand or speak up or put it in the chat.
Hey, Eric, that was a great talk.
Oh, thank you.
Why didn't you go to SMU?
What's that?
Why didn't you go to SMU? It seemed like you'd be a perfect fit there from what you've shown.
Probably. I happen to live in Colorado,
Oh,
Colorado School Mines is a little more convenient,
okay.
and
Makes
they
sense.
also funded me, so that helps.
Good place to hang.
Not
What
too
are you
bad.
gonna do? What are you gonna do when you finish?
That's a good question. I'm trying to actually finish up this coming spring semester. And so I've been actively applying to different jobs in industry with the USGS and some of the national labs. So I'm looking to go into the geothermal energy sector, either doing research or working in industry.
Sounds like you'd make a good professor.
I've thought about that. If I could fall into a tenure track professorship right here at Colorado School of Mines down the street from my house, that would be perfect. But that might be a little bit challenging. And of course, have a fully funded geothermal research group too. That would be great.
Okay. Good luck.
Oh, thank you.
Have you heard of any good examples of just the local geothermal being used at the industry level? I thought that was an interesting application, being able to use geothermal energy for, say, a data center or a refinery or a big plant of some sort. Has that been carried out anywhere yet?
That's a good question. I mean, all of those examples, those aren't things that I just happen to like light bulb come up with. They're out there. People are actively working on them. Like I mentioned, the heavy oil extraction, that was a series of publications that the BEG published in the 80s, looking at some of the heavy oil fields in South Texas. The direct air capture, CO2 sequestration stuff, that's come from a couple of companies. I had a company earlier in the year reach out to me because they were interested in doing this on the Gulf Coast and wanted to see how practical it would be to power their units with thermal energy and electricity with that. So that came from those companies. There was a company in South Texas looking to use one of those salt diapiers for hydrogen storage. They want to, since a lot of these salt diapiers are already being used for different types of storage. Our strategic petroleum reserves are in the salt diapiers. But we store a lot of things in these solution caverns. So there's a company that was looking to produce green hydrogen and stored in one of these. So could we actually use that electricity? Could we use these diapiers to make electricity and produce hydrogen? The data centers one has popped up a couple times. I think companies like Pervo and Ormat are talking to people, or talking to like Google and other tech companies that have a huge demand for power for AI and cloud data and things like that. So a lot of these things are just already out there. But since we do potentially have these resources on the Gulf Coast, we could be doing all these things on the Gulf Coast. We just have to, actually prove that these resources are viable.
Cool. And we do have a couple more questions in the chat. Have you noticed any early lessons learned based on this year's implementation of Colorado's deep geothermal well rule? This is from Jared Ware.
Could you repeat the first part of that? I didn't hear it.
Are there any early lessons learned based on this year's implementation of Colorado's deep geothermal injection well rule?
I'm not familiar with that rule. If you could maybe provide some light on that.
Jared, I'll let you chime in.
Hey, good afternoon. Hey, a fantastic presentation, Eric. That was
thanks.
Awesome. Yeah, we're working on the deep geothermal injection well rule here in Texas, and we just we got the final comments for the shallow geothermal rule. So this is awesome timing for your presentation. But Colorado had implemented their shallow and deep rule in August, and we were looking at kind of what's going on in Colorado to kind of guide us as we start updating our rule here in Texas for the deep geothermal injection wells. So that was the background of my question.
I should probably be more familiar with some of the new regulations that are coming out there. But yeah, I'm not up on that one yet. I've been too laser focused on Gulf Coast geology. But yeah, I'll look into that. I do know some people in the regulatory groups here in Colorado, so I'll ask them about that at our holiday party on Wednesday.
Okay, cool. Thanks.
Yeah.
And then we have another question from Ken. Is the lower temperature as measured on logs all due to the well drilling? I'm guessing that's the correction of the actual to the measured temperature. That's probably due to time of circulation, all those kind of things too.
Yeah, I mean that's the general idea. You know, as we're circulating mud while we're drilling, we're cooling the well bore. Obviously, I mean that's part of it, and we're cooling down the formations around there. And it's kind of tough though. The data set I'm looking at, you know, ranges from shallower wells, you know, let's say shallow, you know, 5,000 or 6,000, 7,000 feet. And then I have those deep wells, those handful that are down at 20,000 feet. And, you know, there's just so many variables that go into these bottom hole temperature correction or measurements, you know, of course, type of mud we're using, how fast we're drilling, the time spent circulation, which is in some ways kind of an ambiguous number based off the different well log headers I've looked at. And then, you know, I think surface temperature at the time of logging is important. You know, if it's below freezing in South Texas in December and we're putting cold mud back down the hole, you know, that might have a more of an effect. There's well vintaging, you know, these deep exploration wells that were drilled in the 70s down to 20,000 feet were probably drilled pretty slowly. So maybe there was time for that mud to equilibrate to the formation temperature. So maybe those wells don't need as much correction. And so there's just so many factors that go into it. It you know, makes you want to pull out your hair. And so using one of these off-the-shelf correction methods, I would say is okay. And that's all we have right now. But the chapter I'm working on right now in my dissertation is on bottom hole temperature correction and subsequent temperature mapping. And, you know, kind of the end conclusion that I have here is for geothermal, where we need to be more accurate understanding these formation temperatures, because we need to know down to, you know, a 5 to 10 degree window, what temperature water are we producing out of the ground. We need to know that exact temperature that's coming into the power plant, because that's going to have an effect on the power plant efficiency, ultimately how much electricity you can produce. And if you're off by, you know, a factor of 10, 15%, you're not going to meet your power purchase agreements. You're not going to be able to make as much electricity as you want. So the in conclusion that I'm having here is it might be time for us to try to develop a better set of intra-basinal correction methods or intra-formational correction methods based off whatever geothermal reservoir you're going to go after, because there's just so much ambiguity with the bottom hole temperature data.
Great point. Thank you. I think we're at about 1 o'clock. If there's no more burning questions, we'll let everyone go. Thank you so much, though, Eric. Like I said, I found this really interesting, especially since we're familiar with a lot of these formations in the geology.
Yeah, no, I mean, thanks for inviting me and letting me talk here about geothermal. And you know, it's just something that I've gotten really excited and passionate about recently. So I like sharing these ideas, and I want people to start thinking about, you know, this sort of energy source in all of our oil and gas producing provinces, not just the Gulf Coast.
Great. Thank you all so much.
Yes, thank you.
Thank you, Eric.
Yep, have a good one.